Today I thought I'd spend 45 minutes just reviewing the review sheet. So reviewing what you have or should have learned this semester. And so you'll get to see that. A few comments. So firstly, we had the poll yesterday and many of you have responded. I like the fact that each project was liked by several people. That's good to see. Uh, Many of you were proud of your projects. That's good. That's very good. And feel like you could have done better. It's always good to do that. I agree. Many of your classmates are very smart, very good. I really appreciate the fact that you enjoyed having mathematical ideas with real world applications. Okay, so that's good. And okay, good. At least one person likes vegetarians now, because I was a little bit disturbed to see nobody likes vegetarians and lots of people like eating vegetarians. So I was a little bit afraid for my safety, right? But anyway, so that's the poll. A quick reminder. So the you're expected to learn about the projects and write in your own words. Okay. I do not want to see essentially the same thing copied by different classmates in your answer sheets. It's very easy to see plagiarism, and that will be grounds for at least severe punishment, if not failure, if I see that. Okay, so just learn a little bit. We'll give you actually more than 6 options. I'm not quite sure exactly how many options, but you'll get more than 6 options to choose from. Okay, so learn something about something. All right. So let's begin the quick review for today's class. And I'm just going to go through the topics. Okay, so think of this as a reminder for what you should have learned. And also, please, before tomorrow's class, please fill in the review sheet. So please fill in every topic, your review sheet, because we'll be using this review sheet for the coupon system tomorrow. So you can ask for help from each other and from the instructors. Okay. So first of all, chapter 7, you learned about matrix basics, how to multiply matrices, proofs of properties of matrix multiplication, distributive law for matrix multiplication, probability matrices, probability transition matrices. So if today there's a certain probability of something happening, tomorrow there's some conditional probability, so how to analyze that. Then we had rotations via matrices, skew symmetric and unitary matrices, so special types of matrices, right? Symmetric, skew symmetric, and unitary matrices. Diagonal identity triangular matrices, so other types of special matrices. The basic step-by-step method of doing Gaussian elimination, so you should all know this. Proof of row equivalence of Gaussian elimination. So if two systems are row equivalent via Gaussian elimination, then they have the same set of solutions. Why is this the case? And how to use Gaussian elimination to solve systems of linear equations. Elementary row operations. So what are elementary row operations and the corresponding elementary operations via matrix multiplication? How to represent row operations via matrices. Row equivalent systems. So these are systems which are equivalent under Gaussian elimination. Row echelon form. This is a special form of the matrix which has zeros in the bottom left, right? It gets you into a triangular matrix. Types of solutions: one, infinitely many, or no solutions, right? Reduced row echelon form. So it's a special type of row echelon form which is diagonalish. It's kind of like a diagonal matrix. Linear independence, and how to check for linear independence of row or column vectors. What is the rank of a matrix and how to compute it, to show that row rank equals column rank, right? Theorems about ranks and proofs of these theorems. So for example, a matrix is invertible if and only if the rank is full rank, right? So things like that. So some Gaussian elimination, row operations by matrix products. Okay, vector spaces. How to check whether a set is a vector space or not, right? So the conditions for a vector space. Examples of vector spaces. To showing things are vector spaces or not vector spaces. Bases and subspaces and spans of vector spaces, right? So if we have a vector space, then a subset of a vector space may or may not be a vector space. We want to check for that. So vector spaces for matrices. So row spaces, column spaces, null spaces. These are all vector spaces associated with matrices, right? Okay, then how to relate solution sets of homogeneous and non-homogeneous systems of equations to the corresponding vector spaces. So, for example, for a homogeneous set of equations, set of linear equations, the solution space is the null space. For a non-homogeneous solution, if there is at least one solution, then it's that solution plus any vector in the null space, right? Then the rank nullity theorem, which told us a relationship between the rank of a matrix, the nullity of a matrix, and the number of columns of a matrix. So rank plus nullity equals n. And how to prove it. So computing row, rank, row space, column space, null space, nullity, checking for linear independence, and various things to do with that. Then Gram-Schmidt orthonormalization. So given a set of vectors, how to end up with a set of vectors with the same span, but which are perpendicular to each other, right? Then determinants, basic properties of determinants and proofs. So for example, interchanging rows of determinants multiplies the value of the determinant by -1 and other such properties. So using these properties to find the value of a determinant, Leibniz's rule, so viewing a determinant as a sum of permutation, sum over permutations of products of elements in that permutation. The Laplace expansion for the determinant, so expanding determinants via smaller determinants. Rank properties of determinants and proofs. So how is the determinant of a matrix related to the rank of a matrix? For example, if you have a square matrix and the determinant is non-zero, that must mean it is full rank and vice versa. But other properties as well. So proving properties of ranks under matrix addition and multiplication, right? Kramer's theorem, so how to solve systems of linear equations via determinants and a proof of this. Methods of finding determinants, determinant of a Cauchy matrix. So this is a matrix where each entry is of the form 1 over xi plus xj. Matrix inverses and basic properties. So AB whole inverse equals B inverse A inverse, things like that. And then necessary and sufficient conditions for matrix inverses to exist. For example, the determinant should be non-zero, the rank should be full, and things like that. Then Gauss-Jordan matrix inversion. So how to find the inverse of a matrix via the Gauss-Jordan method, which is to write the matrix and then the identity matrix next to it, and then do row operations to make the matrix A into the identity matrix, and whatever the I matrix becomes is the inverse of the matrix. So example on how to use it. Matrix inversion via determinants. So how to find the inverse of a matrix using the cofactor expansion of a matrix and proofs. Properties of matrix inverses, proofs, and then some exercises to do with that. Then some properties of general inner product spaces. So more general than just real or complex spaces. So for example, if you have function spaces, then some properties are always true. Cauchy-Schwarz inequality, triangle inequalities, parallelogram inequality, equality, proofs of these things. So something about function spaces. So for example, how to compute the inner product of two functions via taking an integral of that product. Then some bonus questions about function spaces. So how to orthonormalize functions and things like that. Linear transformations. So how to view a matrix product as a function which takes a vector to another vector, right? And examples of linear transformations and null spaces. More about linear transformations. So compositions of linear transpositions is the same as matrix products. So if you're doing matrix like a vector times a matrix 1 times a matrix 2, that's the same as the linear transformation corresponding to matrix 1 operated on the vector, and then the linear transformation corresponding to matrix 2 operated on the resulting vector, right? And then again, some more Gram-Schmidt orthonormalization. And the corresponding equivalence between row operations and Gram-Schmidt orthonormalization. Very nice observation by one of you guys. I think Bob. LU factorization. So this is a game question. So how to write any matrix as a product of a lower triangular and an upper triangular matrix. Function spaces. So yeah, just some more about function spaces and how to. I think this one was about derivatives. The derivatives of function spaces, the derivatives of sines and cosines, and how that's a linear transformation. Yeah, some more functional spaces. Um, so, so then chapter 8 started. So then we started talking about eigenvalues. So one motivating example was the stationary distribution of a stochastic matrix. So a stochastic matrix represents the probability transitions for a random process, right? So to see what this random process converges to. So in the end, if it reaches equilibrium, what's the probability distribution corresponding to the corresponding to this? This is called a stationary distribution. Um, Probability transition matrices, some exercises to do with that. Eigenvalues, eigenvector definitions, and how to find them. So ax equal to lambda x, how to find the lambdas via the determinant by the determinant of a minus lambda I, and then find the roots of the characteristic polynomial. And then the eigenvectors are the solutions of the null spaces of a minus lambda I. Okay, eigenvalues and eigenvectors of 3 by 3 matrices, eigenvalues, eigenvectors, Fibonacci sequences via eigenvalues and eigenvectors, matrix eigenvalues, more of those. Okay, repeated eigenvalues, but with zero defect. So when you have as many eigenvectors as the dimension of the matrix. And then properties of eigenvalues and eigenvectors. So for example, if you have two eigenvectors for the same eigenvalue, then they form an eigenspace and other related properties of eigenvalues and eigenvectors. Okay, so more about matrices with repeated eigenvalues and zero defects. Eigenbasis. So how to find the basis of a vector space, which is the eigenspace, which are the eigenvectors of a matrix, and the use of this. Then algebraic and geometric multiplicities. So algebraic multiplicities are the number of times an eigenvalue is repeated. Geometric multiplicity is the number of eigenvectors associated with an eigenvalue. Some more applications of eigenvalues and eigenvectors. So for example, stretched membranes and population growth models. Then some more eigenvalues and eigenvectors, how to calculate them for Markov processes, powers of matrices by diagonalizing matrices, principal axes via eigenvalues and eigenvectors, some population growth models, some properties of eigenvalues and eigenvectors for symmetric, skew-symmetric matrices, and orthogonal matrices, eigenvalues, eigenvector definitions, and then eigenvalues, eigenvectors, rotations and inversions via orthogonal matrices or unitary matrices, properties of orthogonal matrices, eigenvalues of eigenvectors of symmetric matrices, and then product of eigenvalues. Okay, so yeah. So the trace of a matrix is, which is the sum of the diagonal values, is the sum of the eigenvalues, and the determinant is the product of the eigenvalues. So how to prove this? Eigenvectors of a symmetric matrix, eigenvalues of the inverse of a matrix, eigenvectors for symmetric matrices, eigenvectors for skew symmetric matrices, eigenfunctions. So eigenfunctions for the differential operator, distinct eigenvalues. So if you have distinct eigenvalues, then to prove linear independence. Diagonalization for matrices with zero defect, powers of matrices, more diagonalization of matrices, unitary matrices. So these are generalizations of orthogonal matrices, right? So more about unitary matrices, matrix diagonalization, okay, full rank, omission, and unitary matrices. Orthogonal complements of vector spaces. So given a vector space and a subspace, how to find the orthogonal complement of the subspace in the vector space. How to, and some exercise. The spectral theorem for matrices with zero defect. So if you have a symmetric matrix with zero defect, then it has an eigenbasis. Uh, General symmetric Hermitian matrices. So the generalization of the spectral theorem for general symmetric matrices or Hermitian matrices. So how to show that symmetric matrices always have a eigenbasis. Um, Question about Hermitian skew symmetric and unitary matrices and their eigenvalues and eigenvectors. Schur decomposition. So how to write matrix as a product of an upper triangular and a lower triangular matrix. Schur decomposition and matrix diagonalization. Finding Schur decompositions. Generalized eigenvectors and Jordan canonical forms. So if you have a matrix with non-zero defect, if you don't have enough eigenvectors, then you can still always write it in Jordan canonical form. So then you have a block Jordan form, and how to find this. So examples of these things. Then a singular value decomposition, which several of you use for your projects. So how to write, even if you have a rectangular matrix, how to write it as, how to write the matrix AA transpose as the sum of the singular values times the corresponding eigenvectors for the singular matrix. Examples, and then some applications of these things. Yeah, so some bonus questions proving that the singular values are always non-negative. Properties of singular values, and then the Frobenius norm. So how to show that the singular value decomposition, like choosing the top singular values, gives you most of the energy of the corresponding matrix. So applications of this for compression of matrices, right? So thinking of an image as a matrix, as a rectangular matrix, and then doing a singular value decomposition for this. Some of you guys use this for your projects. So proofs of singular value decompositions. Yeah, image compression example, pseudo inverse of a matrix and orthogonal projections. So why an orthogonal projection acts as can be viewed as a pseudo inverse of a matrix. So some exercises to do with these, how to compute these various things. Matrix exponentials. So to find the exponential of a matrix, you can diagonalize it and then take the exponents of the diagonal of the matrix and then multiply by the corresponding P matrix exponential P inverse. Normal matrices. So these are the most general class of matrices that are diagonalizable. So if A dagger equals A dagger A, then these are called normal matrices. The pseudo inverses of matrices and how to find least square solutions to systems of equations. So to find a solution to a system of equations which has the smallest error, if you have some noisy observations, how to find the smallest error solution. So something more about SPDs. Okay, so that was it about chapter 8. So you know, eigenvalues, eigenvectors, and generalizations of these singular values and so on. Then chapter 9 was basics of vector differentiation, right? So what are the basics of vectors, and then how to use vector properties to prove things about geometries, for example, medians and so on. Dot product basics, what's the definition of a dot product, and properties of these things. Projections, so how to view the shadow of a vector on another vector as a projection, how to compute it via a dot product, the relationship to Gram-Schmidt orthonormalization, to find the shortest distance of one point to a plane by projection, right? So, so again, you can take the projection of a vector onto the plane, subtract this out from the corresponding vector, you get the perpendicular vector, and so on. Definition of cross products. So basic properties of cross products. So given two vectors in three-dimensional space, the cross product of these two vectors is a vector which is perpendicular to this and has magnitude, which is the product of the magnitudes times the sine of the angle between them. Scalar triple product. So this is like a dot product of a vector with a cross product of two other vectors. This represents the volume of the tetrahedron enclosed by the three vectors, just like the cross product represents the volume, the area of the parallelogram enclosed by two vectors, and some other applications. Then some keep exercises to compute these, some more exercises to do the basics of vectors and how to use them. Okay, then we started showing you maxima. In fact, we showed you how to use maxima to do vectors, how to plot vectors, how to plot functions, and then back up in linear algebra, we showed you how to use maxima to compute, to multiply matrices, add matrices, solve matrix equations, find the null spaces, find the determinants, find the characteristic polynomials, find the roots of the characteristic polynomial, find the null space, find powers of matrices. So various properties of matrices and linear algebra can be done via maxima, which you should all know. Then in vector differentiation, how to plot things via maxima, so functions via maxima, direction fields via maxima, right? Then some proving properties about cross products, formulas for dot and cross products for 3 and 4 vectors. So one of these was asked in the midterm, so you guys should be comfortable with these things. Using maxima to plot curves in parametric form, surfaces in parametric form, or explicit or implicit form. So parametric, explicit, or implicit form for each of these three. Then some exercises to do with these things. Vector fields. Okay, then some geometry, in 5-dimensional space, how to find the nearest plane to a 3-dimensional space and 5-dimensional space. So examples like that. Parametrization of a curve, the tangent line of a curve length by taking. So if someone gives you a curve r of t as xt comma yt, then the derivative of rt, which is x prime t y prime t, is the tangent vector to the curve at the point t. And then you can find the length of the curve by integrating r prime t dot r prime t square root dt. Then properties of various things to do with scalar and vector derivatives of functions. Then partial derivatives of functions and properties to do with that. Then, okay, tangent vectors, curve lengths, okay, something about curves of a cylinder, lengths of curves, and so on. Showing that the shortest path joining 2 points on the surface of a sphere is a geodesic. So this is the path followed by airplanes when they're flying, right? Calculating the length of a curve. Then the arc length parametrization. So how to parameterize a curve, not in Cartesian coordinates or polar coordinates, but in arc length coordinates. So in terms of units of ds. And then examples of parameterization for a Mobius strip, calculating arc length, deriving, okay, then acceleration, so velocity, acceleration, curvature, torsion, so different properties of curves that can be computed via different formulae, both via the explicit parameterization and the arc length parameterization. So both of these should be doable. Some exercises to do with these things. Coriolis acceleration. So how to, if you're in a rotating frame or a moving frame, how to measure the acceleration that you feel in the frame and the component of this acceleration due to the movement of the frame itself, due to the movement of the coordinate system you're sitting in. Some exercises to do with that. So shortest path in a sphere. Okay, then the multivariate chain rule and the mean value theorem. So how to use the mean value theorem for functions in multiple variables, and how to use this to find bounds on, for example, the values of functions. Partial derivatives via chain rule. So for functions of many variables, scalar or vector functions, how to compute partial derivatives, and if you're on a surface and so on. Directional derivatives and the gradients and proofs. So the directional derivative is the derivative of a function in 2 or more variables in a particular direction. So given a scalar function and a particular point and a particular direction, there is the derivative, the slope of the function at that point in that specific direction. The gradient is the directional derivative in the direction of maximum descent, right? It's also, if you view the curve in implicit form, then it is the surface normal vector. So these are two different ways of thinking about the gradient, either as the directional derivative of the function in explicit form in in the direction of maximum descent. If it's in implicit form, then it's the surface normal vector. And then how to find the directional derivatives. So surface normal vectors, and then tangent planes, how to find the tangent plane via the surface normal vector. So given a vector which is perpendicular to a plane, you can find the plane, and since you know the gradient of the surface normal vector, you can find the tangent plane, right? Then how to use gradients for gradient descent. So how to find maxima and minima of functions numerically via this iterative process called gradient descent. Just take short steps in the direction of the gradient, right? Linear regression via gradient descent, multivariate optimization. So given function and two or more variables, how to set the gradient to be equal to 0 in that region, and then check the region and check the boundaries of the region, and thereby find the optima, the maxima, the minima of the function in the region. Yeah, so some exercises to do with that. Then the divergence of a function. So given a vector function, the divergence is a scalar function. This measures whether a vector function is compressible or not. If the divergence is 0, then it is incompressible, right? So you should have seen the relationship to fluid flow. So if the divergence is 0, then the fluid flow is incompressible, right? And the Laplacian, so the Laplacian is something like the double derivative of a scalar function. It can also be viewed as the divergence of the gradient of the function. And the Laplacian of a scalar function equal to 0 is a very important equation in electromagnetism, in heat flow, in a variety of different applications. So this was to do with that. Some exercises to compute these. The curl, so the curl of a vector field measures how much the vector field is twisting. That's why if the vector field has 0 curl, it is called irrotational. So an irrotational vector field has 0 curl, right? And then some how to compute this, and some relationships between the curls, the divergence, gradient, and Laplacian, so different properties relating these. Then yeah, some exercises on these, directional derivatives, love curves, gradient descent. So each of these you should have been able to do. Approximation of functions with bounded gradients. So you can do this via the Cauchy-Schwarz and triangular inequalities, and then do something. The relationship, so the equivalent of the second derivative test for functions in 2 or more variables. So in 2 or more variables, you can have points with zero gradient, which are neither the maximum nor the minimum. These are so-called saddle points. So they're the maximum in one direction, but the minimum in a different direction, right? So these are called saddle points. And the relationship to eigenvectors. So the corresponding Hessian matrix, if it has one positive eigenvalue and one negative eigenvalue, then it has a saddle point at that point. Yeah, some practice midterm questions, which hopefully you should be able to do. Rotations, how to compute compositions of rotations, singular value decompositions, linear transformations. So the principal axis of an orthogonal transformation, how to find the axis of rotation. So gradient, divergence, velocity, acceleration, curvature, torsion, solution to systems of equations, symmetric matrices, Schur decompositions, Jordan canonical forms, Gram-Schmidt, least squares, Hessians, computing curl, divergence, Laplacian, all of these in cylindrical coordinates and spherical coordinates. So how to compute these vector derivatives in different coordinate systems. You should be able to do that. Okay, all right. So that was it for the materials up to the midterm. Then after the midterm, we started doing fields. So what does it mean for a set to be a field? So the properties of a field, how to check whether it's a field or not. Euclid's algorithm. So Euclid's algorithm helps you find the inverse of elements in a field. And prime fields. So this is one example of a finite field. So if you add 2 numbers modulo a prime number, or multiply 2 numbers modulo a prime number, then you have a prime field. Addition and multiplication tables, multiplicative inverses of elements, similarities and differences between finite fields and real and complex fields. So much of linear algebra is similar, but there are some important differences. In particular, it is possible. It is impossible for matrix equations to have infinitely many solutions. You can have zero null space, but in that case, you'll have a finite, but greater than one number of solutions to these equations, right? Also, the length of vectors and angles between vectors don't make sense. You can define the norm of vectors via the Hamming norm and the Hamming distance. You can compute the distance between two vectors by the Hamming distance. Um, you can compute matrices, determinants and inverses of matrices, solve systems of equations over finite fields, various properties, row space, column space, rank nullity over finite fields, and so on. How to, yeah, so one application of finite fields, so codes. So how to define a simple error correcting code to correct errors over finite fields, right? So for example, Hamming codes or erasure codes or codes with Vandermonde matrices, so Reed-Solomon codes. So these are examples of codes over finite fields. Polynomials over finite fields. So if someone gives you a polynomial in one or more variables, if you choose the variables uniformly at random from the finite field, then the short-zipper lemma helps you compute that the probability that the polynomial equals zero. One of you use this for your network coding project, right? An example of how to use finite fields for secrecy. So suppose you want to communicate information secretly from one point to another, how to use finite fields for this. Finite geometry. So what does it mean to have points, lines, planes in a finite geometry, right? MDS codes, so linear minimum distance separable codes, an example of that. The singleton bound, so how to prove that given a number of code words in a code, the minimum distance cannot be larger than a certain amount. Message authentication with shared secrets. So, so suppose you have a shared secret, then how can you check that the message that you've gotten is indeed the transmitted message? No one has tampered with it, right? Then Piazza bonus question about secret sharing. So suppose you have some nuclear launch codes. You want to make sure that enough honest people can launch the missile, but if there are too many dishonest people, they don't learn anything, or if there are not enough dishonest people, they don't learn anything, they can't launch it either. So how to do this by codes. Hamming bound, so bound also on the number of vectors in a code by for a binary code. The GV bound, so how to construct codes over the binary field. Extension fields, so instead of just binary fields, if you have extension fields, instead of just prime fields, if you have prime power fields. So for example, 5 square, 7 cube. So there are fields with these sizes, but then you have to use polynomials over the base field and then define the corresponding addition multiplication operations. Irreducible polynomials, how to compute them, and then how to use maxima to do finite field calculations, right? All right, so that was it for finite fields. Then we moved back to vector calculus, in this case, vector integral calculus. So how to compute a line integral and exercises to do with that. Applications of line integrals to compute the work done. And then how to check if a line integral is path dependent or independent. So if you can find a potential function, if you can find a function such that the vector function whose line integral you're trying to take is the gradient of a scalar function, then the corresponding function is path independent, right? Then path independence, some exercises to do with this. Then path independence, okay, I don't understand this. Yeah, I think there's something to do with the connectedness of, so if the region is simply connected, then you can use the potential function method to argue that a closed curve is if there's a potential function and the region is simply connected, then a closed curve line integral is zero, right? Then one exercise, the ML inequality. So a rough bound on a path integral via just calculating the maximum value of the function times the length of the curve. Then multivariate integrals. So how to compute integrals of multiple variables. Double integrals. So this you should have studied in an earlier class as well, but a quick review. So how to integrate functions in two variables twice, and the interpretation of this as the volume under a surface, right, or the volume of an object. Changes of variables for functions in two variables. So using the Jacobian and then using a change of variable formula and changing the limits of integration to do this. So some exercise to do with this, some applications, finding the volume. So Piazza bonus question, n-dimensional spherical coordinates and how to find the Jacobian for this. The parallel axis, perpendicular axis theorems and the stretch rule. So how to use double and integrals to prove things about the moment of inertia of objects. Then Green's theorem. So this is sort of the Green's theorem in the plane. This is the equivalent of in two dimensions of the definite integral. So how to relate the integral over a closed curve to the double integral inside the curve, right? Appropriately defined. How to verify that, the normal derivative form of Green's theorem, the flux integral. So the flux integral is a vector integral. It measures the amount of fluid flowing through a surface. Another form of Green's theorem in the plane. So using the normal derivative form and other forms. Laplace's equation and relationships to Green's theorem. So an application of Green's theorem, how to find the area of a surface. One of you guys did a planimeter project based on this, right? But there are other applications as well, finding the center of mass, finding the moment of inertia and so on. The normal vector and tangent plane. So there are two different ways to find this. One is via taking the gradient. The other is by taking parametrization of the surface and then differentiating the parametrization according to the two parameters, taking the cross product of those two things, and then finding the corresponding normal vector. Sometimes this is easier. Integral of vector functions, integrals of scalar functions, so surface integrals of vector and scalar functions. One is a flux integral. The other is like computing the mass of a surface or the charge on a surface or so on, if you're given these mass or charge densities. How to prove Pappus's centroid theorems. So these are theorems that tell you the surface area or volume of objects which are generated by rotating other objects, right? And how to prove this via Green's theorem or other theorems. Some surface integrals. The divergence theorem. So the divergence theorem helps you relate double integrals to triple integrals, and then verifying Gauss's divergence theorem, and exercises to do with that. Relationships to potential theory. So different applications to heat theory, I forget, but there are many applications in the videos. You should look them up. Stokes theorem. So this is a generalization of Green's theorem, and it helps you relate a general flux integral, vector surface integral to the corresponding line integral along the boundary, and verifying that and proofs, and functions for which Stokes theorem are not applicable. So if the region isn't simply connected, or things like that, then it's not applicable. Then there was that question to do with the Beautiful Mind, the movie The Beautiful Mind, which showed a relationship between vector spaces, curls, gradients, and Stokes theorems. I still haven't seen a solution. I do encourage you to try it if you haven't had a chance yet. Helmholtz decomposition. So in physics, if a vector field is decaying sufficiently quickly, then you can always write it as any vector function as the sum of the gradient and the curl of a function. So this is a useful decomposition. And then things to do with the parameterizations of surfaces and areas. All right. Finally, the last week. So sets of numbers. So countable and uncountable numbers, rational, irrational, algebraic, transcendental numbers. Um, then cardinalities of sets and exercises to do with this. Limits of sequences. The definition of the limit of a sequence. Cauchy's convergence criterion. So if you don't know the limit, then how to check whether a sequence is convergent or not. The Bolzano-Weierstrass theorem, which says that if you have a bounded sequence, a bounded infinite sequence, then it has a convergent subsequence. The limit of a function, which says that for any epsilon greater than 0, there should be a delta greater than 0, such that f of x minus f of y is less than epsilon if x minus x naught, if x minus y is less than delta. Continuity and uniform continuity of a function. So the limit should exist everywhere, then it's continuous. And if the same delta works everywhere, then it's uniformly continuous. Continuity of functions in two variables. This is subtle. This requires you to check all paths in the neighborhood of a point. So this is really a subtle concept, right? Continuity and uniform continuity of functions. So suppose someone gives you a sequence of functions. Well, okay, so uniform continuity, then there was something more to do with that. Limits of multivariate functions. So we saw this. Then pointwise versus uniform convergence of a sequence of functions. So we saw that even if you have a sequence of continuous functions, the limiting function may be discontinuous, right? And that's because you had pointwise convergence, but not uniform convergence. So, so both these notions of convergences of sequences of functions are important. The derivative defined as a limit f of x plus delta minus f of x divided by delta, limit of delta going to 0. The mean value theorem. So the mean value theorem tells you the relationship between the values of a function at 2 points, the 2 points themselves, and the derivative in between. And generalizations of the mean value theorem, so Rolle's theorem, Cauchy's mean value theorem, and so on. How to prove L'Hopital's rule via this. Taylor's theorem. So Taylor's theorem can be proved via the mean value theorem. It helps you approximate a function as higher and higher degree polynomials. So this is useful in many applications. Yeah, Cauchy's mean value theorem. Remainder terms for Taylor's series. So how to estimate the error in your estimate of a function if you do the Taylor series expansion. Riemann integrals. So how to define the integral of a function via Riemann sums. And usually we do this actually via upper and lower Darboux sums. So find the area of the rectangles below the curve, find the area of the rectangles above the curve, and then take the limit as the mesh size goes to 0. Riemann integrals, remainder terms for Riemann integrals, and so on. And also keep exercises and how to use maxima for various things like this. Like for example, how to use maxima for Taylor series and things like that, right? And then some bonus questions like the ergodic theorem. So how to show that if you take multiples of irrational numbers, then it becomes dense in, so multiples of irrational numbers modulo 1, for example, becomes dense in the unit interval. And one exercise to do with that. All right, then private information retrieval. So how to get some information from a server without telling the server what information you're interested in. Planimeter, how to compute the area of a curve just by looking at the boundary. So Google's algorithm, PageRank algorithm via eigenvalues and eigenvectors, and how to look at special things that can happen, spams, spider traps, and so on. How to create a schedule, so how to view this as a linear optimization problem, how to do it via linear programming. Cryptography, so the Michaelis crypto system, so the connection between codes and cryptography, how to hide information by codes. principal component analysis for face recognition. So how to do PCA, which is related to SVDs, and then how to use it for face recognition. Just by using the largest singular values and the corresponding singular vectors and comparing for the same image. Network coding, how to mix information together in a network to make sure it gets through, and the relationship to linear algebra. So there are connections to the Schwarzschild lemma, finite fields, and so on. Game theory, so if two people are playing a game, how to represent the game as a matrix, and how to figure out the expected return for each player, how many points are they going to get. Talking piano, so suppose someone is talking, how to take the Fourier transform and how to map this to keys on a piano so that the piano can pretend to talk, right? Quantum mechanics for search algorithms, so how to use a quantum search algorithm, Grover's search algorithm, so the relationships to the unitary transformations, projection operators, and how to find an object in far fewer than n queries. Image processing, so how to blur an image, how to sharpen an image, how to merge images together using ideas from linear transformations. Image compression via wavelets, so how to compress an image by taking an orthogonal transformation, wavelets, which help you detect edges, and then use further ideas like zero-tree decompositions, perhaps Huffman coding, and then perhaps also multiple description coding to make sure that the even if you lose some packets, you can still get a reasonable reconstruction. Least square fitting, so given a bunch of data and a model for the data, so linear, quadratic, or higher degree polynomials, how to compute the corresponding low degree approximation to your data. Fast matrix multiplication, so given two matrices, how to multiply it faster than the naive algorithm, how to invert matrices faster than the naive algorithm, how to multiply two polynomials faster than the naive method by using the fast Fourier transform. All right, wow, even just reading out the topics took a lot of time, but I expect each of you to have filled out this review sheet by tomorrow before class. If you do not fill it out before class, well, you'll have to go to the back of class and fill it out while the other people get coupons to ask each other questions and ask us questions, okay? So please fill out this review sheet or update the review sheet. So if by now you understand more about pre-midterm questions and would like to update your scores here, then please fill those out as well or update those as well, okay? But that's the expectation for tomorrow. So that's it for now, and let's close this baby.